Hi, welcome back. This is Mrs. Mays, and today we're going to talk about black body radiation and the photoelectric effect. First of all, let's talk about what is black body radiation. What's a black body? Well, basically we're just talking about any old object. All objects emit some sort of electromagnetic radiation, even if you can't see it. So in the picture behind me, you'll see the Photoelectric lava flow, and it's glowing because it's so hot. But a lot of objects emit radiation, even if you can't see them glowing. So something that's just sitting there not glowing, not showing any color at all, it's still emitting a radiation that we can detect. And so even if it's black, it's still sending out radiation. So the intensity of this radiation and the specific spectrum is going to vary depending only on the temperature of the object. The hotter it is, the more intense the radiation. Did I spell temperature right? Temperature. Sure, that looks good. Okay. So, for example, in the picture that's behind me, the temperature of this lava flow can be estimated by observing its color. The more red it is, the cooler the lava, and the brighter, sort of yellowish white that it is, the hotter it would be. Let's look at an example of the black body spectrum of other objects. So let's look at how temperature affects the spectrum that we see. So what I'm going to do here in this simulation is increase the temperature, and look what happens to the spectrum. See, we can observe the intensity of the radiation goes higher, and this is radiation from the sun when it's really hot. This is in Kelvin degrees, so if we were hotter than the sun, we would have much more intense radiation. Now let's cool it off to light bulb intensity. So if we have radiation the intensity of a light bulb, look how tiny that bump is. Let's zoom in a little so we can see that spectrum better. So for a light bulb, if we're all zoomed in, a lot of the radiation that we can observe is, let's see, can I get a pen that we can see? Let's try this. There it is. See, this radiation is not even in the visible light spectrum. This would be infrared, so it's like heat radiation. And then there's this portion here that's in the visible light where we would see white light. And that's good, because if we didn't have white light coming from our light bulb, it wouldn't help us to see any objects when we turn it on. So let's get a little bit cooler than that. Let's cool off. Cooler than a light bulb. We'll go down to an oven. Oh, wow, look how flat that is. So zoom in a little more. Where's our biggest bump? It's past the red in the spectrum. Past the red is what we call infrared. So we don't have a lot of visible light, and that makes sense. If you looked inside your oven, you could feel the heat, but you wouldn't actually see it glowing. You might see the coils inside your oven glow, but the oven itself isn't really glowing. It's not putting out a bunch of light, but it is putting out a lot of heat. That's how we cook our food in there, right? Okay, let's cool it way back, way down. The temperature of, say, the Earth, like weather types of temperatures. I gotta zoom way in, get closer, because it's not very intense radiation. And I think we should probably zoom out on our x-axis. Oh, yep, because I zoomed in too far. So we're basically looking at radiation that occurs in longer wavelengths in a much lower frequency, and that should also make sense. When you look at the Earth, it's not glowing with visible light. Here's our visible light way over here in this band, but the Earth isn't sending out rainbow colors, and it's not sending out light like a light bulb does. So that should make sense to us. That's what the spectrum looks like for black body radiation. The problem is, this type of spectrum that scientists observed, it just didn't really match what they thought they understood about light and the universe and particles in general. So classical physics just didn't really explain very well the shape of the spectrum of these black body radiations. Since the spectra didn't fit the predictions of the theory that describes light as a wave, then we had to come up with some other way of describing light. And so there was a guy named Max Planck. In 1900, Max Planck explained it by assuming that atoms would only emit radiation in quantum amounts. You see, Max Planck wondered, like, if the smallest unit of matter is called a molecule, like water molecules, for instance, then couldn't there be a smallest unit of energy? A container of water holds billions of water molecules, and so maybe energy holds lots of little tiny pieces of energy. And so his postulate is that energy and frequency are directly related to one another. And he tested this by doing lots of experiments with the photoelectric effect. And he found out that the amount of energy corresponds to some constant called h, now we call it Planck's constant, times the frequency of the light. So let's be clear. H stands for Planck's constant. It's a number 6.63 times 10 to the negative 34 joules times seconds. And then the nu, remember this Greek letter, is called nu. That stands for the frequency of the light. So when you're looking at energy, it's going to have a specific frequency that corresponds to that amount of energy. The higher the frequency, the more energy it has. So let's do an example problem. In this example, it says, whoa, go back. What is the energy of a photon that has a frequency of 240 gigahertz? You maybe have heard of gigabytes on your computer, so gigahertz, that's a really high frequency, right? So we know the equation for energy is E is equal to H times nu, where H is Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, and then the frequency, nu, is equal to 240 gigahertz. That would be 240 times 10 to the 9th power hertz, and hertz is the same as 1 over second, or per second, right? So now it's time to solve. Let's substitute our values into the equation E equals H nu. So E is equal to 6.63 times 10 to the negative 34 power joules times seconds, multiplied by 240 gigahertz. So 240 times 10 to the 9th per seconds, and then we'll multiply. When we multiply our units, joules times seconds, multiplied by 1 over second, the seconds cancel away. And now I need my calculator. Remember how to use scientific notation? So we're going to use the E button on the calculator, and I get this number, 1.59 times 10 to the minus 22 joules. It makes sense, doesn't it, that energy should have units of joules, and the negative 22 joules is not a real great amount of energy, it seems like. But it's just one single photon, right? And so a beam of light would have billions of photons in it. Let's try another one. This question's asking, what is the frequency of a photon that has an energy of 8.0 times 10 to the minus 18 joules? So I'm solving for frequency, that's my target, and my equation is that E is equal to H times nu, Planck's constant times the frequency. Now, what do I already know? I know the value of E is 8.0 times 10 to the minus 18 joules. I know the value of Planck's constant. H is 6.63 times 10 to the minus 34 joules times seconds. And the thing that I don't know is the frequency. I'm trying to figure that out. So I'm going to take my equation here, and we're going to rearrange it so that I can get frequency by itself. H is multiplying nu, so to get nu all alone, I have to undo multiplication. Let's use division for that. So I divide both sides by Planck's constant, and I get the frequency is equal to energy divided by H, divided by Planck's constant, because these H's over here canceled away. Now I'm ready to put my numbers in. E was 8.0 times 10 to the minus 18 joules times seconds. And then H is always going to be the same number, 6.63 times 10 to the negative 34. Oh, shucks, I did that wrong. Joules times seconds is the units for Planck's constant. It's just joules for energy there. All right, time for the calculator, right? Remember to use the E button to do scientific notation. And I got 1.21 times 10 to the 16 per seconds, which is to say 1.21 times 10 to the 16 hertz. That's my frequency. We got these units of per second right here where joules canceled away, and we just had seconds in the denominator. That's the same thing as hertz. Okay, I just want to be clear. When you're using the calculator for scientific notation, we're looking for a button that has EE on it or above it, so you can solve scientific notation problems without any trouble. So what did all of this mean? We know how to solve the problems. That's not the hard part. The hard part is, like, what does quantum mean anyway? Planck's quantum hypothesis basically states that there's only certain frequencies of light that were emitted, and he noticed this by doing experiments. He would shine energy, he would shine light onto metals, and only certain amounts of energy could actually get that substance to release light, and it only came in certain frequencies. Not any old frequency would do. So it's like if you were to turn a dimmer switch and nothing happens until all of a sudden it's just brighter suddenly. Or we could think of it as like going upstairs. Quantum theory is kind of like stairs. You can be on step number 5 and you can be on step number 6, but you can't stand on 6.5. There is no 6.5 step. You can have 1 foot on 6 and 1 foot on 7, but you can't actually stand on 6.5. You're either on 6 or you're on 7 or you're on 5, but you're never anywhere in between. And that's what quantum theory says the electrons around atoms do. You see, when light strikes a metal, then the electrons sometimes fly off. This word sometimes is really important. And when they fly off, we get electrons to move, which means we have an electrical current. We can measure that electrical current. So I've got a picture down here. Here's my light shining onto my metal, and here's the electrons flying away. But it only happened sometimes. For every different type of metal, the amount of energy was a little bit different, but there were certain energies that could get the electrons to move, and some energies that just wouldn't do it. And classical physics could not explain some of these features about how this effect worked. So Einstein is the guy who used Planck's idea about quantum theory, his quantum postulate, to solve the problem. Here's what Einstein said. He said, well, Planck's onto something. He said there's a piece of light that's the smallest piece that you could have. So if atoms can only emit light in little packets of energy of specific sizes, then maybe the light itself travels as packets of energy that are given by Planck's formula, E equals h nu. This was a radical new theory, that there would be packets of energy or packets of light, And Einstein called these packets of light photons because this prefix photo is Latin for light. That's what that word means. So basically, what we came back to is that we've shown light is made of particles. Particles that are called photons. Therefore, light is not a wave, it's a particle. Now, some of you might be thinking back to where we were in our previous podcast. Earlier, we proved that light is a wave. In the double-slit experiment, we proved that light is a wave. Remember Huygens? He was proved correct. But now, we've proven that light is a particle. So now Isaac Newton can be verified or validated. His theory was correct. And we've proven that light is actually both a particle and a wave. Let's look at wave-particle duality. How does this work?
We see particle-like behavior every day. Drop a ball on the ground and it follows a single trajectory. Leave your giraffe parked on the street and when you come back, it's still there, just one giraffe. And we see wave behavior too. Toot your horn and waves spread out through the air, carrying sound to the ears of anyone around. Or drive a boat through water and waves travel outwards along the surface. But when it comes to the physics of the very small, what we see is a wave-particle duality. Sometimes very small things, we're talking electrons and protons here, behave like particles, and sometimes they behave like waves, flip-floppers. For example, if you release an electron, it'll travel outward as a wave through the room, but when it hits the wall, it'll only hit in one place. You started with one electron, after all. So what if sound had a wave-particle duality? When you shouted, the sound waves would spread outwards in all directions, but only one person could hear what you said. Or when you drove your boat through the water, the waves would travel like normal, but only hit the shore in one place. Now that would make for some pretty boring surfing.
So light actually exists as both waves and particles. We take advantage of this in electron microscopy. Wave-particle duality is exploited so that we can see very, very small objects. Objects that are smaller than the wavelength of visible light can be viewed when we use electrons. Things like, here I have pollen, and I have the head of an ant, and then here are some red blood cells. Oh, that's it for the photoelectric effect. Next time, we're going to talk about matter and its wave properties.